Hey guys, welcome back. In this video, we're going to be talking about the acid-base properties of water. And when I say this, we're actually going to be talking about the auto-ionization of water. So if you think of what water, right? We have H to O, H, plus H. Right? So if I have two waters, what can happen, if we talk about the Bronsted-Lowry definitions, right? This H here, right, can go to one of these lone pairs, all right? And so on the other side, we can get hydronium and hydroxide. All right. So most of the time, we'll just write it as H2O liquid plus H2O liquid going to your hydronium and your hydroxide. All right. So now, if we were to write the equilibrium constant expression for this, we'll have it K, and it'd be KW for water. And that would equal your concentration of hydronium multiplied by your concentration of hydroxide, which is at 25 degrees Celsius, 1.0 times 10 to negative 14th. All right. So that would be the ionization of water. Well, what does that mean? All right. Well, when we talk about water and whatnot, there's properties, and we wanted to know how much of hydronium and hydroxide, right? So we got hydronium here, and we have hydroxide. Well, hydronium is the solvent cation. Hydroxide is the solvent anion. And the ratio of those two can determine things in water, right? Is there more hydronium? Is there more hydroxide? And those are conditions when we talk about like pressure, temperature, volume, molarity. Well, the amount of hydronium or the amount of hydroxide are also part of the conditions. And sometimes those conditions are vitally important for reactions. Sometimes they don't matter, but sometimes they matter a lot, all right? And so we are going to take this expression, all right, and because it's negative, right, exponent, it's a small number. These concentrations are less than 1 typically, right? 1 molar and less. They can be more, but most of the time we're going to talk about less than 1, okay? 1 or smaller. So we don't get 100 molar H+. We don't get that. But definitely, you can actually have 10 molar H+. So, but we're going to start with 1.0 molar. And to make numbers easier, because this number right here is not very easy for us, 1 times 10 to negative 14. We don't like that number. To make it easy, we'll take the negative log of everything. So we take the negative log of everything, right? And we're going to make that P, right? Some of you know where this is going. So we take the negative log of KW would equal the negative log of the concentration of hydronium, all right, plus the negative log of concentration of hydroxide would equal the negative log of 1 times 10 to the negative 14th. Well, that happens to be 14, right? That's 14. So we're going to say that the pKw equals what we're going to call pH plus pOH equals 14. All right? So we're going to make a little table here of this. But first, if we know the concentration of, how about this? The concentration, this number is here, right, for Kw. If these two are equal to each other, what are they? All right, well, what's the square root of 1 times 10 to the negative 14? 1 times 10 to the negative 7 molar, right? And so this is not a huge number, 1 times 10 to the negative 7 molar, right? That's not big. That's not a huge concentration. But at neutral, when these are, oh, no, don't want to do that. When these are the same, right, we have what we call neutral water, and they're 1 times 10 to the negative 7 molar. But what if they're not the same? So we're going to talk about the acidic conditions, and basic conditions, all right? So if we are acidic, that means the concentration of hydronium is larger than the concentration of hydroxide, all right? And if we are basic, the concentration of hydronium is less than the concentration of hydroxide. That kind of, the opposite makes sense. So let's talk about this. So we got pH. We'll do 0, 0, 1, 2, 4. We'll do 7. And then I'll do 9, 11, 12, and 14. All right, so this would be neutral. These are acidic. And these are basic. Okay. All right, so let's talk about our concentration of hydronium here. So the negative log, what would this be? Well, this would be 1.0 molar. Then we have either 0.1 molar or 1 times 10 to the negative 1, right? 10 to the negative 2 molar, 10 to the negative 4 molar, 10 to the negative 7 molar, 10 to the negative 9th molar, 10 to the negative 11th molar, 10 to the negative 12th molar, 10 to the negative 14th molar. So that'd be 1.0 times 10 to the negative 14. That's what we have, our concentrations. Now, the pOH is the opposite. All right? And so we would start off with 14 and then 13 and then 12, right? Because 0 plus 14 is 14. 1 plus 13 is 14. 2 plus 12 is 14. All right? And then we got 10, 7, 5, 3, 2, 0. All right? And our concentration of hydroxide, right, we start off at 1.0 times 10 to the negative 14 molar. Then we got 10 to the negative 13 molar, 10 to the negative 12th molar, 10 to the negative 10th molar, 10 to the negative 7th molar, 10 to the negative 5 molar, 10 to the negative 3, 10 to the negative 2 molar, and finally 1.0 molar hydroxide. All right. So at neutral, when we're neutral, our hydronium concentration equals our hydroxide concentration. Now, for whatever reason, we almost always talk about it in terms of pH. All right, probably to avoid confusion. Are we talking about pH or pOH? Well, we're always going to talk about pH. All right, and so how this is calculated, right? The pH is equal to the negative log of the concentration of hydroxide, or H plus. All right, and then to get the other way, if you have the concentration of H plus or H3O plus, right? It is 10 to the negative pH. And same thing with pOH. pOH is equal to the negative log of the concentration of hydroxide. That means the concentrate, right? If you need to solve for the concentration of hydroxide, it is 10 to the negative pOH. All right. And so we're using this scale because we're actually counting by an order of magnitude here, right? These are orders of magnitude. So it's kind of like if you ever lived where there's earthquakes, right? The Richter scale is logarithmic like this. And so a 2 to a 3 or a 3 to a 4, right? It's just not one unit, it's 10 times, right? So a 7 to an 8 magnitude earthquake, it's a big jump. It's a huge jump, right? It's not just, it's just one. No, it's 10 times more, all right? So each of these, like this is 100 times, 2 to a 4 is 100 times more hydronium. 100, actually, in this case, it's 100 times less hydronium, right? Because we start off at 0 is the most concentrated, to 14 is the least concentrated hydronium. The base is opposite. So when the pH is 14, it's mostly hydronium. Or certainly, when the pH is 14, it's mostly hydroxide. It's hydroxide, right? And so these conditions, whether you're acidic or basic, they play a role in reactions. Like for us, we have to be in this region, a little bit past 7. Our blood has to be 7.4-ish, right? We don't want it. We don't want a pH of 4 in our blood. We don't want a pH of 11 in our blood. Those would be very bad days for us, all right? Well, day, because that would be it. We want 7.4, all right? So that's where our blood pH needs to be, all right? And so these conditions are really important, all right? I hope that makes sense to you guys. If you have any questions, feel free to reach out. Otherwise, we'll see you next time.